Alright, so in this lesson we are concerned with a certain kind of force and, and the ways that we can use that force in order to calculate some things. So this force is a stretching force, so this is changing the shape of an object, usually a string or a spring or a rope or something like that that can stretch a little bit, or a lot, depending on the thing. Really, it could refer to any substance that's being pulled on, any kind of object that's being pulled, but usually, most of the time, we talk about it being springs. But just be aware that you could talk about this with just about any object that is being stretched, including rubber bands or elastic waistline or things like that. This picture is taken from a website. You can see the website right there. Just as a side note, almost all of the images I use in these videos are public domain and readily usable for this sort of purpose, but I couldn't find one like that of one of these devices, so I just went ahead and took this one. You can see it came from this website, dhgate.com. All right, just so you can tell I'm using proper attribution of my sources. So let that be a lesson to you when you're doing your stuff and citing your sources. Okay, so here's a picture of a guy, very muscular. He's working out and he's using one of these stretching pieces of equipment. And it's got a bunch of springs, actually. There's, I think, 7 of them on this one. And he's basically pulling on them, so they're under tension, is what it's called when you stretch an object. The stretching effect, the force that causes the stretching effect is called tension, right? So, or a tensile force or something like that. So force of tension, that just means it's stretching, all right? Now, in terms of what we're talking about here, it's called Hooke's law. And Hooke's law states that the amount of stretch of the object is proportional to the force of tension that's applied to the object. So what do I mean by that? Well, here's one example, and this is an image that you've seen once before in a previous video. We've got the same spring in 3 different scenarios. So here we've got 1, here we've got 2, and then here we've got scenario number 3. So in scenario number 1, there's nothing on the spring. All right, it's just hanging free, no load applied, it's just there. So this is what it looks like, the spring, the length the spring has when there's nothing, there's no force, there's no stretching force applied to this spring. All right, situation number 2, we now have a weight, a mass at the end of that spring. It's attached there. So now we've got a new situation, right? There's a force acting on that spring. It's the force of weight of this mass, okay? And then it causes a stretch, right? And they labeled the amount of stretch there. They just called it X, okay? Because we don't know how much mass this is. We don't know the length of the spring, but we can tell that the length has changed by that much, so that we call that X, the amount of stretch. All right, it's very important. What we're concerned with here is how much the spring stretches, not what its actual length is. All right, so we're interested in the length here, right? This total length subtracted from the initial length, so the difference there is X. Okay, now let's suppose we add another identical mass to this one. Same exact mass, same weight. Then we'd have situation number 3. Here's one mass, here's another mass. They're both attached, and the stretch there would be double X, 2X. Okay, so basically that just says the stretch is proportional to the force. Okay, this is what it would look like if we graphed it. Now this graph is not related to that previous image, although it could be. Basically, you can see here the proportionality. If you add 1 Newton of force for this one, 1 Newton of weight, then you should get, in this case, 10 centimeters of stretch, 0.1 meters. If you add 2 newtons, you get 20 centimeters, 3 newtons, you get 30 centimeters, 4 newtons is 40 centimeters. So you can see that the stretch is directly proportional to the force that is applied, and that is called Hooke's law. All right, Hooke's law can be defined by this equation. All right, so it says that the stretch, the force applied is proportional to the stretch, and that proportionality is defined by this equation. And we'll look at that. We're going to look at this in more detail now. Okay, so in that equation that we were just looking at, all right, F equals kx, then here's what we mean by that. All right, this equation, F equals kx. F is the force of tension that is applied to the spring or other object that we're stretching. X is equal to the amount of stretch that occurs. Again, it's not the total length, it's the amount of stretching that has occurred. So it's the change in length that happens as a result of this force. Okay, so it's the change in length, the stretch only, not total length. All right, and then K is the constant of proportionality for this equation. It's called the spring constant, and for any specific spring, the spring constant is just a property of the spring. All right, it doesn't matter within limits, but as long as you're in that proportional range of the spring, you can add whatever weight or mass you want, and the K will not change. K remains the same for any given spring. And of course, if you have two identical springs, they will have the same spring constant. All right, but different springs will have different spring constants. You might have a thick, really tight spring, and then you might have a thin, really loose spring, and those are going to have different values of K. All right, let's do an example. So let's say a spring starts with a length of 10 centimeters when a 5 Newton load is applied. All right, so the length of the spring is 10 centimeters long, and it already has a 5 Newton load on it. All right, so this is our starting conditions. Then we say that an additional 10 newtons of load is added to the spring, all right, and the length becomes 30 centimeters. So then we want to find the spring constant, okay? So we need to find the stretch, all right? First thing we need to do is stretch. So the final length of the spring is 30 centimeters, and the initial length was 10 centimeters, all right? So the stretch, which we call x in this equation, the stretch is going to be 30 minus 10, which is 20 centimeters. All right, so we have our first part. That is the stretch. Now we know the force that's applied, all right, is 10 newtons. So we're not concerned with that initial 5 Newton thing. That's not relevant in this case because that's just an initial condition. So that's our starting point, basically. So we want to know what changes when we add more load. So 10 newtons of load causes the thing to stretch, and now it's going to be 30 centimeters. All right, so just as a side note, this is probably not the most realistic example, but I'm kind of assuming that the spring has a little bit of an initial stiffness to it. Anyway, don't worry about that. Just the main thing I want you to be concerned with in this example is the numbers. Okay, so we had a 10 Newton force. So F in this case is equal to 10 newtons, and it's those 10 newtons of force that caused the 20 centimeters of stretching. All right, so if you recall our equation, let me rewrite it here. Use red. F equals K times X. All right, and we're going to need to rearrange that so that we can solve for K. K is going to equal F divided by X. All right, so we have F is 10 newtons and X is 20 centimeters, which leads us to our answer, which is that, we'll do this in blue now, K equals 1/2. All right? And then you might say that it's newtons per centimeter as the units for that. 1.5, or sorry, 1/2, you might say newtons per centimeter, but you don't really need to include the units there. All right, so in this case, the value of K is 1/2. So we solved the equation, or we solved the problem that it asked us to solve, because it said find the spring constant. So there it is, K, spring constant, in this case, when 10 newtons of load causes 20 centimeters of stretching, that means that the constant is 1/2. All right, awesome. And the last thing for this topic, if we're plotting out, say we take a spring and we keep loading it and we keep loading it and we keep loading it and we keep putting more and more on it, eventually we get past the point where the spring is proportional. Okay, every spring has a limit. You know this from rubber bands. If you take a rubber band and you stretch it too far, first thing that might happen is it gets little damaged spots on it, and it might not go back to quite the same way that it was before. But especially if you take a rubber band and you stretch it too far, what happens? Well, it breaks. All right, so that would be this point. Same thing with springs. If you load them too hard, if you put too much force on them, they will eventually break. Okay? And there's a region here that's called the proportional area, or the proportional region. Here it's called the elastic region. Okay? And then there's a point here. You see that point? Up to this point, it's a straight line. It's proportional. And then we add a little bit more weight, and bam, we get a lot more stretching. The proportionality stops up in this region. It's no longer obeying Hooke's law anymore. All right. So Hooke's law applies to this part of the equation and of the graph, this part of the graph, right, and not to this part. Just to clarify, what we'd be talking about here is force on the axis there, and stretching is on this axis. Okay, so again, this region here is the proportional region where Hooke's law is obeyed. So the point where Hooke's law stops being obeyed, all right, the point where a spring stops obeying Hooke's law, that point right there is called the limit of proportionality. Okay? Limit of proportionality. That's the point where the spring stops obeying Hooke's law, and it is no longer stretching at a constant rate compared to the force that's applied. All right? So there's a vocab term for you, limit of proportionality. You need to know that along with everything else we talked about in this video.